So, welcome back after the short break. What we are discussing is that small signal equivalent circuit with respect to operating point, which is basically linearization. We are talking about how do we once we have the circuit, how do we linearize the circuit and so and so. So, whenever we are considering the equivalent small signal equivalent circuit, if I quickly draw the circuit, we do have the small signal input, and then base to emitter we do have something called R pi, and then we do have the current source, dependent current source. So, either we write in the form of voltage dependent or current dependent. So, this is I C, we may write in terms of I B. In fact, there is another way of writing it in terms of V B E. So, whatever the voltage it is getting dropped across this base to emitter terminal. So, we call this is V B E, and incidentally, since then there is no resistance here, we may say that this is also V B E. And then I C it can be written in terms of V B, and we have seen that it is having some factor which is capital I C by V T, and this is referred as transconductance parameter called G M into V B E. Okay. And then of course, we will come back to this point, and then we do have the resistance R C, and this is getting connected to AC ground, and then of course, we obtain the voltage here. What we are saying is that we have seen graphical interpretation of linearization, we have seen in the form of equation, and also we have seen in the form of equivalent circuit. And whenever we are considering this equivalent circuit, it is, as I said, that this equivalent circuit of the whole common emitter configuration, it involves the equivalent circuit of the transistor. So, if you see this part, this is the equivalent circuit of the transistor. So, this is the base terminal, this is the collector terminal, and this is the emitter terminal. In this case, of course, we do have different elements or parameters involved. Say for example, we already have discussed about the G M. So, likewise we do have the base to emitter resistance R pi, and then we do have the current gain, base to collector current gain, and this is different from beta f. This is actually referred as small signal current gain, so far we are ignoring the early voltage. In case if we consider the early voltage, depending on the voltage at the collector, so it will be having some variation of the collector current. Namely, based on the V C variation, we may be having some variation in the collector current. So, if you consider that part also, then across this current source, so you may say that it will be having some conducting element. So, across this one there will be another conducting element. It is actually it is going to the emitter. So, this conducting element it is referred as output conductance. In this case, as you can see that this we refer as output. So, that is why it is output, it is referred as output conductance, and that is the meaning of each of these terms involved with this equivalent circuit. If you see here, they do have of course their own unambiguous definition. So, whenever you are talking about say GM, which is referred as transconductance of the device. So, how is it getting defined? This transconductance, it is representing the relationship between the collector and VBE. So, you may recall that this collector current IC versus VBE. So, this characteristic curve, it is exponential with respect to some DC point or Q point, we are linearizing it, and this linearization is it is basically a linear segment of the line, and that line can be represented well represented by the slope of the line, and this slope of the line is nothing but the first derivative of this current with respect to VB. So, the transconductance, its definition, it is change in collector current with respect to change in VBE voltage. Note that this is capital I small c, this is capital V small VB. So, if we vary this base to emitter voltage, whatever the variation of this current we are observing, keeping rest of the things constant, this relationship, it is getting represented by this GM transconductance. Since I am keeping other parameter constant, particularly the collector to emitter voltage, we are keeping it constant. So, that is why we are considering this is partial derivative. And we already have in different way we have obtained this GM expression of the GM, it is capital IC divided by VT. In fact, if you use the expression of this IC in the form of IS C e to the power VBE by VT, and then if you take the derivative of first derivative of this expression, what you can get is you will be getting this is IC divided by VT. Okay. And this IC, of course, it is instantaneous IC, which is the slope, of course, it depends on the instantaneous value. But then if we restrict our discussion within a small range, then we can say that this IC can be well approximated by capital IC, namely whatever the current we do have here at the DC operating point. If you consider this slope of this line, probably throughout this one we can assume that slope is remaining constant, and hence you may say that okay, this is capital IC divided by VT. So, that is what we obtain here, the expression of the GM, it is capital IC divided by VT. On the other hand, whatever the current it is flowing through this circuit in the small signal equivalent circuit, if I say that this current is flowing through base to emitter terminal or rather base terminal is say IB. So, if I vary this voltage, this current is changing. So, you may say that if I take ratio of these two, then we may say that yes, it is basically the base to emitter terminal conductance. So, if I see the conductance here, namely if I observe the variation of the base terminal current with respect to VB, then equation wise dou IB divided by dou VBE. So, that is the input port or base to emitter port conductance. If I take reciprocal of that, that represents the base to emitter resistance, it is R pi. Later I will see why we do have different subscripts, but at least we understand that the unit here it is ohm. So, we call this is base to emitter resistance. And again, if you use a expression of this IB in the form of IS B e to the power VBE by VT, and then this part, the internal part, it becomes this is IB divided by V t, and then we may approximate that this I b, it is with respect to the q point. So, we can say that this is capital I capital B divided by V t inverse. So, depending on this I b, of course, this value of this resistance it will vary. So, in fact, it is intuitive. If you see, whenever you are observing the let me use different color. So, whenever we are observing the I b versus V b characteristic curve. So, depending on the operating point here, we may get some slope here. So, that gives us 1 by r pi at that point. Now, if I come some other point here, of course, the corresponding slope here it will be different. So, obviously, at this point the corresponding r pi it will be different. But as I said that if we restrict our discussion or our experiment with respect to some operating point, then you may say that okay, this r pi it is remaining constant. So, based on the DC current there I b, capital I b, we can say its resistance is V t divided by I b. So, likewise, the other parameter if you see here, namely the beta naught. Beta naught, of course, you may say that sometimes we assume this beta naught it is quote and unquote close to or equal to beta f, but strictly speaking it is having its own definition, and normally we use beta naught as the symbol which represents the relationship between the collector current variation with respect to base current variation. So, obviously, this is different from ratio of capital I c by capital I b. In fact, normally what it is used here, instead of writing here dou I c divided by dou I b, the relationship it is fairly linear, but whatever it is normally written in this form of small I c divided by small I b. And I like to say here one thing that if the beta f it is remaining constant for whatever the range of this I c and I b we are considering, then we may say that beta naught it is same as beta f. But in case if the beta f it is different, then obviously depending on the operating point their dependency it will be different. So, ideally if we plot say I c versus I b. So, I c along the y axis, and this is along the x axis is the I b. So, if you see both of them are having exponential relationship, and so it is expected that if this both are exponential, both are having exponential dependency on the same parameter called V b, then obviously it is expected to be it will be linear, and slope of this line of course it will be the beta f. But in practical case, actually if you go to lower level of current, it is having a different slope. Here it may be remaining constant, and then again if you go to higher current, again it will be having a bend. I will not be going detail of the sources of those nonlinear part, but as long as if you keep the transistor within certain range, or if I say that if I consider range of this collector current within say few hundreds of microampere to maybe 10 milliampere for normal transistor, you may say that this range it is fairly constant. So, if we are within this range, so wherever we consider slope remains constant, and this if I say that if I extend it, if it since it is going through the origin, then the large signal beta f and beta naught they are same. But if you are say somewhere here, obviously the slope here it will be different, which is the beta naught it will be smaller than this one. Likewise, if you consider the upper side. So, if we sketch the variation of the beta, either beta f or beta naught with respect to say I c, what you can say that in the middle range you may say that it is remaining fairly constant. If you go very low current, it may drop, and likewise if you go to higher current, it may drop. This is the violation of low level injection, and this is where the recombination current starts also becoming prominent. Somewhere in this range, you may say that low level injection is valid, as well as the recombination at the base region it can be ignored, and hence both of these curves are having quote and unquote same kind of relationship, and hence the beta is remaining constant. So, that is about the beta. And if you consider on the other hand the other parameter, particularly this conductance part, as I said that the source of this conductance is basically the early voltage, or you may say if you consider this circuit, if I vary this collector voltage, namely VCE voltage, due to early voltage, let me use different color, due to early voltage effect. So, this I c is having some dependency on the VCE. In other words, if I say that if we observe the collector current while varying the VCE, it is having a increment of the current. In other words, you may say that if I vary this, if I increase this voltage, the total current is increasing, which means that the total current, it is not just completely defined by the condition at the base. In fact, some part it is also dependent on this one. And since where if we change this voltage and if you are observing the same terminal current, you may say that if I take the ratio, namely change in the current with respect to change in this voltage, that gives nothing but the output conductance. So, that is why we are saying here the output conductance G naught is defined by change in the collector terminal current versus the collector to emitter voltage. And sometimes either we put this element in the form of conductance, or some people are writing in the form of output resistance. So, if I take reciprocal of this one, that gives us the output resistance, or rather 1 by output resistance is defined by dou I c divided by dou V c E. So, in fact, if you see again to get the expression of this part, you require the expression of this I c. So, I s c into e to the power V b e by V t. Now, I have to consider this additional factor, namely 1 plus V c e by V a part. Then only I will be getting this part is not zero. Okay, this slide looks very clumsy. So, let me clean up the rest of the things. I guess you will remember. Just to have a little more discussion on this one, let me clean up the slide here. So, we are discussing here, and we have to take, as I said, we have to take the expression of the collector current I c, which is having I s c reverse saturation current e to the power V b e by V t multiplied by 1 plus V c e divided by V a. Now, if I take the derivative of this equation, particularly partial derivative with respect to V c e, and then of course, since we are changing only this one, not this one. So, you may say that this part it is remaining constant, only this part it will be changing. So, if I say that if I take the derivative of the whole thing, this part we will be taking out, and then we do have dou this part divided by dou VCE, and that gives us this ISC into e to the power VBE by VT divided by VA. Now, we may approximate this whole thing by the collector current IC. So, whole thing, of course, collector current is having this part, but since this part is appearing as is, so we may say that this part is very small compared to 1. Only while you are taking derivative, we are considering this part, and then this part it is IC and this is VA. So, the expression of G naught, it is basically IC divided by VA. So, we can say that all these parameters, new set of parameters, they are dependent on the operating point. Okay. And as the operating point we are trying to keep it constant. So, we may say that for small signal equivalent circuit, these parameters you may say that quote and unquote remaining unchanged. So, whenever we will be drawing the small signal equivalent circuit, first step of course, we need to find this parameter, and to get that, first thing is that we have to find the operating point. So, let us see what we can summarize here. So, as we understand from our previous discussion that whenever we are linearizing a nonlinear circuit, we are essentially drawing small signal equivalent circuit. And while we are drawing the small signal equivalent circuit of an amplifier, we are replacing BJT by its small signal equivalent model. And this model involves a certain set of parameter device, we call it as device parameters, and they are given here. As you can see here, we do have transconductance defined by small signal collector current divided by small signal VBE, and then the base 2 emitter impedance, which is defined by VBE divided by IB, small signal base current, base terminal current. Then current gain, small signal current gain, which is defined by IC divided by IB. And then output conductance, which is 1 by RO, output resistance. So, that is defined by change in IC or small signal IC divided by VCE, small signal VCE. So, all these parameters, as we have discussed, that they depends on the operating point, or to be more precise, if we express these small signal parameters in terms of the operating point. So, the GM, it is IC, I capital C collector current at the operating point divided by thermal equivalent voltage VT. So, likewise, when you consider R pi, and since it is VB by IB, so it can be written in the form of IC. So, we can replace this IB by beta naught by beta naught by IC here, and then we do have the VB, and this part it is the 1 by GM. So, the expression of GM we can write here, or we can say that the expression of R pi equals to beta naught into VT divided by IC. So, where beta naught is given here, the small signal current gain. Likewise, when you consider G naught, and its definition is given here, and it can be expressed in terms of once again its operating point, namely IC divided by the device parameter early voltage VA. So once we have the small signal parameter, they can be represented by a small signal equivalent circuit, namely base to emitter we do have R pi, and the current entering to the base, it is IB. Voltage drop across this R pi, it is VBE. So this VBE, on the other hand, it is producing a current at the collector terminal. So collector to emitter, we do have voltage dependent current source, which is IC equals to GM into VBE. So we do have, this is the collector terminal, and this is base terminal, and this is the emitter terminal, and then also from collector to emitter we do have finite conductance, so that is G naught. So this is G naught. So this is what the small signal equivalent circuit. Now this small signal equivalent circuit, it will be very useful while we are converting the say actual circuit into in terms of its small signal equivalent circuit. Now let's see how it can be deployed, or what is its application. So let's see what is its validity. What is the validity of this? Now here we do have the small signal equivalent circuit of the BJT, and let's try to see that how it can be utilized to get the gain of the circuit. So along with the small signal equivalent circuit of the BJT, let us also integrate the other components of the circuit, namely the RC, and then instead of connecting this to VCC, let you consider this is AC ground. Likewise, at the input we do have the input signal which is applied at the base with respect to a DC voltage, but for small signal we consider this DC voltage, it is 0. So this is V in, small signal input, and then at the emitter we, of course, it is connected to ground, and whatever the voltage we will be getting here with respect to the ground, so that you call it is output, and whatever the output you are getting here, it is the small signal or the signal output. So if we analyze this simple circuit, we can find the expression of V in, V out in terms of V in. So incidentally, this VBE of this circuit is equal to V in. So the output voltage, if you see this circuit V out, it is the output resistance RC, which is coming in parallel with R naught, which is, of course, R naught, it is 1 by Gm. So this multiplied by the current, and the current flowing to this node, it is Gm into VBE. And if you see the polarity of the current, and if I consider this is the polarity of the developed voltage, this is plus and this is minus, then we'll be getting a minus sign here. So as a result, and also of course this VBE, it is V in. So by combining this equation and this equation, what we are getting here, it is the expression of V out. I'm writing the expression of the V out here by V in. equals to minus Gm into Rc in parallel with R0. So this is nothing but the voltage gain of the circuit AV. So that's how the utilization of the small signal equivalent circuit. So let's move to one numerical example to further illustrate on this. Cover maybe highlight one numerical example and so in this numerical example, if you see we do have the same basic circuit. The main thing is at this bias we do not have any resistance. So, directly the voltage you are applying both the bias as well as the signal to the base. So, that makes the circuit simple and then we do have say supply voltage is say 10 volt and let you consider this VB as such that the current here it is say 10 microampere. So, I am giving this VB in terms such that the IB capital IB it is 10 microampere and then say beta of the transistor it is say 200 beta A for beta whatever you say and so that gives us the quiescent current here it is 2 milliampere. Now, to get a good linearity range here namely to get good linearity range here we like to keep the operating point well away from this point as well as whatever the saturation limit or active region limit. So, this is maybe the maximum voltage we can have here it is 10 volt. So, load line it is intersecting there at VCC which is 10 volt. This voltage it is very small, you may approximate that this is 0.3 volt. So, roughly even if you are keeping this voltage say at 5 volt, we do have good linearity range of this output IV characteristic. So, if we do have 2 milliampere of DC current is flowing for this base current and this beta, then we may say that we may prefer to have 5 volt roughly 5 volt drop across this RC. So, that gives us this resistance maybe 2.5 kilo ohm. Okay. So, suppose these informations are given. So, what I have done here it is in fact there are maybe two ways of framing the numerical problem. Either we give this information and then directly we can ask draw the small signal equivalent circuit, find the values of the small signal parameters and then find the small signal voltage gain. Or probably we can give this bias condition such that this is 10 microampere, this may be given to us, then find this operating point and then we can go into this one. But whatever it is, just for your practice instead of say let you consider instead of 2.5 which is giving us exactly 5 volt, let we consider this is something different maybe 2.2 kilo ohm which is a practical value, 2.5 normally we do not get. So, probably you can try out find the operating point namely the IB it is given, collector current is also very straightforward. Then you can find the VCE voltage which is nothing but V capital out also and then you can find the value of the small signal parameter GM considering the early not early the thermal equivalent voltage to be 25 millivolt. So, this is IC divided by VT. So, this is 2 milliampere divided by 25 millivolt. Then the R pi it is not required. So, still you can write R pi equals to I b divided by V t. So, this is 10 microampere divided by sorry, this is reciprocal of that. So, 25 millivolt and it is reciprocal. So, that gives us 2.5 kilo ohm. By the way, the base to emitter resistance, you can see that it is much higher than typical diode on resistance, mainly because the base current, though it is having exponential dependency, the base current is very small. And then we may assume that early voltage it is very high. So, you may say that output conductance it is 0, and then beta naught you can approximate to be beta f, which is 200. So, from that you can find what will be the small signal voltage gain. The small signal voltage gain, it is if I consider magnitude, it is G m into R c, and G m into R c is 2 milliampere divided by 25 millivolt multiplied by 2.2 kilo ohm. So, this part it is 4.4 volt divided by 25 millivolt. So, that gives us 4.4 divided by 25 into 1000, right. So, whatever the value it is coming. We have observed that linearization of nonlinear circuit containing some transistor is important, because we are looking for linear behavior. Then you may say that then why are you looking for nonlinear circuit? Nonlinear circuit gives us amplification, possibility of amplification. So, the nonlinear behavior, say like exponential behavior, it gives us highly good gain. In fact, this is one of the source of one of the factor which is giving us good gain. So, we require nonlinear circuit, but then we are looking for linear circuit. So, that the output signal nature it will be same as the input signal nature. And then what we have done is that since you are looking for the linearization, through that we are getting something called small signal equivalent circuit, which is basically linearization of the total circuit, keeping our constraint, namely with progress of time DC wise the operating point should not change, only the signal part it will change with time, and also the average of the signal should be 0. So, that the operating point or the quiescent point should not change. So, that gives us some different notion called small signal equivalent circuit. Now, whenever we are drawing some small signal equivalent circuit of a given circuit, the same notion it can be deployed for the simple transistor also. So, whatever if I consider BJT in this case, if I restrict our signal within some range, then the BJT transistor can be represented by a linearized form, which is referred as small signal model of the transistor. And why do we go for small signal model of the transistor? That simplifies the analysis. So, of course, to get the model parameter, we have seen model parameter it depends on the operating point. So, it is having different set of parameter, but once we get the value of those parameters, and if we know that quiescent point is not changing, then we can make use of those parameter value, and then small signal model of the BJT or small signal equivalent circuit of the complete circuit, it will be basically simplifying the analysis and calculation. Okay. This is the heart of analog circuit. So, today we have discussed primarily on BJT. So, similar kind of discussion it will be there in our next class on MOSFET.